next vector operation that we are going to discuss is called curl, and it allows me to represent or the line integral of the electric field around a closed path in point form. Okay. In electrostatics, this is fairly, the integral of this E dot dl over a closed path is equal to 0, it is very trivial, because integral of E dot dl over any path will tell me the potential difference, and all that this equation is telling is that as long as the electric field remains static, okay, if you go to a closed path and evaluate the line integral, this line integral will be equal to 0, because you are looking at potential difference of one point with respect to the same point. Okay. Now, how do I put this in the point form? Well, to put that in the point form is slightly different from the divergence, because curl operation is a vector operation, that is, it takes vector as input and gives you a vector as output. Okay. So, it will have three components, at least in the Cartesian coordinate system it will have three components x, y and z, and you have to evaluate the curl of all the three components by going to a certain definition. Okay. So, let us look at a path which lies in the xy plane. You can imagine a path that is given by here at this point along this way. The path is oriented in the sense that you need to specify the direction of the path. Now, for any closed path you have two directions. One direction is as you go along clockwise direction or counterclockwise direction, and the other direction will be the clockwise direction. Okay. What we do is we take the right hand rule into account. We say that the path should have its orientation such that if you traverse the path, you will be forming a right handed coordinate system. So, you go from x to y along this counterclockwise direction, the corresponding vector would be along the z axis. Okay. So, this is the path that we consider, and we will label this path as, say, path 1, 2, 3 and 4. Okay. And we will evaluate this line integral over this path. Okay. So, let us get started. How to evaluate the line integral? Well, before that we need to know what the coordinates of the path are. The line integral I am evaluating, eventually hoping to get the point form, will be at this point x y. Okay. And I am going to assume that the width of the path and the height of the path is going to be very small, okay, and the area eventually goes to 0. Okay. Where is the area vector directed for this path? The area vector is directed along z axis. So, which means that I am actually evaluating the z component of this operation curl. Okay. Look at path 1. Along path 1, if you start from the left edge here, okay, and move to the right edge over here along path 1, what you are seeing is that along this path the y value will be changing, however, the x value will be constant, right. If the electric field is a function of all three components E at x, y and z along path 1, okay, which is located at x minus delta x by 2, and path 3 is located at, sorry, this one is located at x plus delta x by 2, and this is located at x minus delta x by 2. Okay. So, along this path that we have, on the path 1 the value of x is constant, however, the value of y will change from y minus delta y by 2 to y plus delta y by 2. Okay. So, it will change from y minus delta y by 2 to y plus delta y by 2. We will assume that electric field is going to be constant. Okay. Electric field is going to be constant over this length, however, the electric field has to be evaluated at point x plus delta x by 2. So, along path 1 the direction of the line element is along y axis, okay, y hat dy, but this is at a fixed value of x, which is x plus delta x by 2, where x y is the point at the center of this path, and this edge path 1 will be along x plus delta x by 2. Along path 3, if you look at the line element will be directed along minus y direction. See, this is in the direction opposite to path 1 direction. So, it will be minus y hat dy. What is the value of x here? It is x minus delta x by 2. Okay. On these paths no other component of electric field is required except the component of electric field along y. Okay. So, you want Ey and Ey on paths 1 and 2. Okay. At these two paths you want to evaluate Ey. At 1 it will be Ey at constant value of x plus delta x by 2, okay. Y can change, and the same E y at path 3 will be given by x minus delta x by 2, and it will change along y. So, this is for path 1, this is for path 3. So, if I now evaluate this line integral, okay, if I evaluate this line integral, the contribution from path 1 or the path 1 line integral will be equal to E y x plus delta x by 2 comma y, okay, multiplied by delta y, because as you integrate from y minus delta y by 2 to y plus delta y by 2, this will get multiplied by delta y, and contribution from path 3 will be E y evaluated at x minus delta x by 2, okay, along y delta y. Sorry, once I integrate there will not be any y dependence. So, this is essentially the contribution from path 1 and path 3. Now, you rather suspect that there is some sort of a slope coming up, and you will be right. This is the electric field component y at two different points, x plus delta x by 2 and x minus delta x by 2, right. They are getting multiplied by delta y, the same multiplier on both sides. So, if you just recall the expression for partial derivative of E, okay, this is the y component of electric field with respect to x, this is precisely equal to E y x plus delta x by 2, whatever the value of y that is there, okay, and E y x minus delta x by 2 at the point y divided by delta x, because delta x by 2 minus delta x by 2 will be equal to delta x, okay. So, this is the width of this one, so it is delta x. So, you can use this definition and replace this E y of x plus delta x by 2 comma y and E y of x minus delta x by 2 comma y from this expression, and you will obtain the contribution from path 1 and path 3 can be rewritten as del E y by del x multiplied by delta x delta y, okay. And if I call this delta x delta y as some delta area along z, the contribution from path 1 and path 3 is basically del E y by del x delta a z, okay. Similarly, you can show that the contribution from path 2 and 4 will be equal to del E x by del y with a minus sign. If you do that one, you will see why there is a minus sign, multiplied by the same area delta a z. Therefore, the integral of this E dot dl with path lying in the z equal to constant plane, which is xy plane, okay, which is the z equal to constant plane, is given by del E y by del x minus del E x by del y multiplied by the area delta a z. Now, what we will do is we do whatever we did very similar to divergence, okay. So, in divergence what we did was we obtained the closed surface integral and divided by the volume and let the volume go to 0. In this case what we will do is we will let the area go to 0, okay, we will let the area go to 0. So, you can go back and write down for the path, this is xy plane, this integral of E dot dl, okay, is given by del E y by del x minus del E x by del y multiplied by delta area along z, okay. Now, divide both sides by delta area z and then take that limit of that area to 0. So, what you get is del E y by del x minus del E x by del y, which is defined as the z component of the quantity curl, okay, of the electric field E, which is written as del cross E of z, okay. So, this del cross E of z, which is the z component of the curl of E, this fellow in the bracket is called the curl of E, okay. This z component is given by del E y by del x minus del E y by del E x by del y, and operationally it is given by integrating the line integral along the path which is lying in the x y plane, okay. So, you need to make this area size go to 0, okay. So, this is the point form for the curl in the point x y at a given value of z, Of course, you can try paths in yz plane, you can try paths in x z planes as well, and you will arrive at the result for del cross E, which will have 3 components. So, there will be a component along x, there will be a component along y, and there will be a component along z. Okay. All 3 components will be there, and we have just evaluated the z component. You can evaluate the x and y component by choosing appropriate paths, and there is actually an easier way to remember this curl. Okay. If you know how to calculate determinants, then this quantity can be obtained by this particular determinant of a 3 by 3 matrix. Here are the partial derivatives. Okay. Note that this row does not make sense unless it operates on some electric field components, and you put those electric field components here. Okay. So, if you evaluate the determinant of this, you will get the curl which will have all 3 components x, y and z. For example, you can check this, right. So, if I want to find the z component, I have to take, for the z component I need to look at the determinant here. So, that would be del E y by del x minus del E x by del y, just as we have obtained. However, I would like you to go back, and this derivation I want you to understand, so that you can actually reproduce the required result for curl without having to remember the determinant. Okay. Or you can use the determinant as a sanity check that you have obtained the correct value for curl. Okay. Doing this in other coordinate systems is also possible, they are slightly tricky, and we will not do that over here. You can refer to the textbooks for the corresponding formulas. Okay. We have now introduced you to 3 different vector operations. One vector operation is the gradient operation, the other vector operation is the divergence operation, and the other vector operation is the curl operation. What are the physical meanings of these operations? The gradient, as we remarked, would tell you that if you consider contours on a hill and consider the contours of constant height, you will see that the contours would tell you, and if you go along the contours or go along the directions in which the slope changes maximum, you will reach the top of the hill or the bottom of the valley. So, this is essentially the gradient physical example. So, these lines which we have drawn are the contours of constant height, and at any point the gradient actually points to the direction of maximum change of slope. Okay. So, it is a vector which tells you how the function is changing along a particular direction. Sometimes this is also called as directional derivatives. Okay. And to reach the top of the hill or bottom of the valley, you would be wise to point, or you would be wise to proceed along the direction in which the gradient is maximum. So, gradient tells you how a function is changing, not in one dimension, but in 3 dimensions. Okay. So, this is the gradient operation. And why was gradient operation important for us? If you take these contours as constant potential contours, that is the value of the potential is constant along these contours, then the electric field was given by the gradient of this potential contours, right. The magnitude of the electric field would be at any point will be the maximum value of the gradient at that particular point. So, you can evaluate gradient at different directions, where the direction is maximum, that would be the direction for electric field. Okay. The second operation that we looked at was the divergence operation. This operation tells you that if you take a closed surface, okay, and then there are flux lines that are coming out of that one, okay, and as you let the surface go to 0, if the value remains constant, okay, then this forms a source. In the context of electrostatics, the divergence of the quantity flux density gave us the total charge enclosed or the total charge density at that particular point. Okay. The final operation that we introduced you to was a curl operation. In order to understand or appreciate curl, you can imagine a field which looks like this. Okay. It could be a water that is moving in a river. Okay. The water level is, or the velocity is pretty high at the top, and as you go down to the bottom, the velocity would be very weak. Now, if you imagine that I have some sort of a paddle wheel here, okay, I can imagine a paddle wheel. Okay, I have been pretty poorly drawing these paddle wheels. What would happen is, on the top of the paddle wheel there is a larger push because of the water current. However, at the bottom of the paddle there is not much of a push because the velocity here is small. So, what would happen is that the paddle wheel would rotate. Okay. Thus, fields which actually rotate are described as having non-zero values of curl. However, fields that would not rotate are called as irrotational fields. Okay. So, when curl is equal to 0, such fields are called as conservative fields or irrotational fields. Okay. And it is actually an interesting thing that this curl equal to 0 is the condition that is required for us to write down electric field as a gradient of a potential function. Okay. The fact that curl E equal to 0 right at any point for electrostatic case allows me to express electric field as gradient of V. Okay. Only when this condition that curl of E is equal to 0 you can actually, or in the regions where this curl of E is equal to 0, you can define the scalar potential. Unfortunately, this equation, right, this del cross E equal to 0 is not valid in the time varying case. In the time varying case, this curl of E will have a non-zero value, indicating that there is some sort of a source, okay, for the electric field which will give the rotation to the electric field. Okay. So, if you have a field which has no divergence, for example, you had a field which we considered which was constant everywhere, right, and it was completely independent of any of the coordinates. So, in this case, if you try and consider a closed surface, there will not be any non-zero value of the divergence. Okay. As you start reducing this one, you can see that there is as much flux entering and as much flux as it is leaving. In fact, this condition that when del dot some vector field is equal to 0, we say that this field is solenoidal or divergence free field. Okay. So, we say that D has no divergence, and in fact, that will allow me to express this D as a vector as the curl of another vector field F. We will in electrostatics have no case to use this particular equation. I am just giving you this as a consequence of vector calculus. Okay. The consequence of this del dot D is equal to 0 is that I can actually write down D as curl of F. Okay. Although in this case we are not going to do that one, for the magnetic field case when we discuss, we will see that del dot B will be equal to 0, and in that case I can use B to define a new vector quantity called as vector potential. Okay. We will see that once we look at magnetostatic case. So, I hope that the physical meaning of gradient, divergence and curl are clear. Gradient tells you the directional dependence of the slope of a function in 3 dimensions. Of course, you can expand it into any n dimensional cases. Okay. So, that is what the gradient tells you, and gradient is related to the electric field because minus gradient of V is the electric field. The minus sign, remember, is only for our reference, which tells us that as we go against the field, the potential would rise. Okay. So, this is the gradient operation. Divergence has 2 things. When the divergence is non-zero, it means that there are some charges at that particular region of space that you are considering, and that would act as the source or the sink of the electric flux lines. Okay. And that gives that relation between the divergence and the charge density at a point is called Gauss's law and is given by del dot D equal to rho. In case del dot D is equal to 0, then it simply indicates that there is as much lines that are going in, as much flux lines that are coming out. However, mathematically it allows me to write down D as curl of some other vector field F. Coming to curl, curl itself is a vector operation which kind of measures the amount of rotation of the field. Okay. So, a simple example of a field which has non-zero curl I have shown here, and if you imagine putting up a paddle wheel, it is like this kids which would play with this paddle wheels. As kids we would play with that one. If you put that one in wind, if the velocity of the wind is different at different points, then the paddle wheel would rotate, okay, indicating that the wind has, or the wind that we are looking at has a non-zero value of curl. Okay. And if the curl of a vector quantity is equal to 0, then we call that field as conservative or irrotational. It is not rotating, and in that case and in only that case, then I can write down the electric field or any vector quantity that I am considering can be written down as the gradient of a scalar quantity. Remember, V is scalar. So, only when del cross E is equal to 0, then it allows me to write down the electric field as gradient of potential. Okay. So, let us look at couple of other equations in electrostatics that we have sort of remember that. One was the Coulomb's law. Okay. Coulomb's law tells me how to find out the force on one charge distribution on a test charge, okay, and we know that this force would act in the direction that would join the two charge distributions, okay, it would act in the line that joins the two charge distributions. At the same time, the field of a point charge goes as 1 by r square. So, Coulomb's law was especially applied for point charges, and we see that the field would go as 1 by r square. Instead of dealing with Coulomb's law, we have introduced fields. Okay. In electrostatics, we have introduced two fields, one is electric field E and the other is the flux density D. In the two cases, we related them. In free space, D was epsilon 0 E, and in case of a medium, we said D is equal to epsilon 0 some epsilon r E, or in general simply some epsilon times E. However, we did not clarify what we meant by epsilon r, nor we told you how to obtain this value of epsilon r for different materials, and that is precisely the subject of next class. Okay. From del dot D equal to rho v, we obtained two more equations which are very important. We will be seeing these equations later when we calculate capacitances. Those equations are called as Laplace equation and Poisson's equation. Laplace's equation is del square v equals 0, and this del square was a vector operator called Laplacian. Okay. Laplacian of a scalar quantity, it is equal to 0 for Laplace's equation. This is Laplace, and this one is the Poisson's equation.